So I'm Mona Vij from Intel Labs, and today on behalf of Graphene community, I'll share our latest on the Graphene project. So here's some quick, mm, I guess, disclaimer from Intel. Um so let me start with the Graphene project summary where we are at today. So Graphene is a library OS which is designed to run unmodified Linux binaries on other platforms. The current focus and effort has been mainly bringing up Linux applications on SGX, but the project is intended to be much broader and can support other architectures and operating systems. And basically, today Graphene supports lift and shift paradigm for unmodified Linux application binaries for confidential compute with Intel SGX. So Graphene is a community maintained open source project released under LGPL. And our project has a very well defined testing and validation criteria. We have CI/CD in place, and the project maintenance is governed by the criteria put together by the community. And Graphene already integrates with the Azure Kubernetes services and can be deployed for protecting applications in cloud environments. While we are not quite ready for production, but we are working towards a production release very actively in Q2 21. And also, you heard earlier from Confidential Compute Consortium, Graphene project has received technical acceptance, but there are a few administrative issues that we need to address before finally joining the consortium. So Graphene is a growing project. We have growing contributor and maintainer community. We have universities, big and small corporations, and individuals contributing to the project in the form of code and as well as overall direction of the project. And we also already have a growing set of well-tested applications. These include machine learning frameworks, databases, web servers, and the language runtimes. So let me just quickly start with a bit of history on the Graphene project, and I'll give a bit of overview of the architecture as well. So the project started as a research prototype in Stony Brook University, and the very first open source version of Graphene was published in 2014. And as I mentioned, Graphene is a libOS where you can run unmodified binaries on other platforms. So Graphene basically pulls in a lot of kernel functionality in the form of a library and links to the application directly. And Graphene and libOSs, libOSs have been around since the early 1990s, and they've been designed to provide compatibility with other platforms. And so they typically have a fairly modular design. So like Graphene has this core library OS, which implements a lot of the Linux functionality and lot of the core functionality, which is platform independent. And then any platform independent code is implemented in this platform adaptation layer. So most of the system calls can be handled within the libOS. It reaches out to the platform adaptation layer only when the host OS must be involved for request for processing. So this reduced user kernel interaction not only provides improved performance, but it's also very suitable for security as it reduces the attack surface because you're leaving the application only on smaller number of calls. And as you can see, today Graphene supports about 166 of the 325 Linux APIs, but that already allows us to run a large class of applications. And these 166 calls are mapped to 15 Graphene APIs, and that are, in case of Linux, it's mapped to 50 Linux system calls. So this modular design for Graphene made it very suitable to port to SGX, and the first port on SGX was done in Intel Labs in 2017. And so the porting to SGX actually involved only developing a new platform adaptation layer. The core libOS is shared amongst with the core Graphene project. So now, since SGX applications have a trusted part and an untrusted part, so the SGX PAL also has a trusted PAL and an untrusted PAL. And basically, this untrusted PAL that sits outside outside the enclave acts as a loader that builds the enclave in the wrapper process. It also loads the libOS, the trusted PAL, and the applications. And it also serves as a glue code to enter and exit the enclave, as well as issue any system calls to the host OS on behalf of the enclave. So similar to other layers, the interface between this trusted and untrusted PAL is also fairly small. We have about 40 or so SGXO calls. And Graphene also takes additional precautions and builds a shielding layer at this enclave trusted and untrusted boundary. And but when we typically talk about trusted execution environments, we also frequently judge the level of security by the lines of code. So in that sense, Graphene also offers a really good solution. The Graphene libOS and the trusted PAL is about 50 to 60K lines of code. And when we and if I guess if you compare that to say tiny configuration of Linux, it's about 270,000 lines of code, and a typical Linux is about 5 million lines of code. So the TCB of Graphene at about 60K lines of code is very small TCB for a framework that can run a large variety of Linux binaries out of the box. So uh, I guess I talked about this Graphene shielding layer. Let me just give you a little bit insight into what are the type of things that we implement at this shielding layer. Uh, Practically all security critical paths are protected against variety of attacks. So just to name a few, we have this idea of trusted libraries. So any library that you want to load inside an enclave, its integrity is verified by checking against a valid hash value. And we also support this other feature called protected files, where the file can be transparently encrypted and decrypted. uh, Graphene also has full support for fork, where migration of the checkpointed state from the parent to the child process is transparently encrypted. All communication between the Graphene processes is encrypted as well. And then we have quite a few additional checks in SGX PAL to prevent against other classes of attacks. And just one item to note is we don't provide any additional network communication protection, because most of the security critical modern applications use SSL or TLS anyway. Um, so while you can run your application completely unmodified in Graphene, Graphene requires you to specify a manifest where you can specify various security policies for your workload. So the effectively manifest specifies the security posture of your application. And so this manifest file is a simple plain text file in a simple TOML format. So let's just look at this example here. You first have to specify what's the actual executable you want to run. So in this example, if you wanted to run a Redis binary inside Graphene, and then with the in the manifest, you can also sort of override the required environment variables. So whatever variables you want to specifically specify, you can mention them here. And then the manifest can also you can specify subset of host directories that needs to be visible to the enclave, and you can restrict it by specifying these mount points. And then in SGX 1.0, there are some restrictions. Today, you have to specify the build the whole enclave upfront. So you can specify the enclave size. And we also can't dynamically add threads in the first generation of SGX. So you need to specify how many threads you want to run in your workload. And typically, when you want to specify any libraries that you want to load during runtime, they need to be specified as trusted files. And Graphene will automatically sort of calculate the secure hashes during build time, will append these hashes to the manifest, and during runtime, Graphene will verify that the files were not modified. So really, manifest is the most important file while enabling applications inside Graphene. So let me give you just a highlight of the number of features that we have in Graphene. So not only you can run your unmodified applications inside SGX, it also provides you a number of features for sort of building this end-to-end protected solution with Intel SGX. So Graphene supports both local and remote attestation, both for EPID and DCAP schemes for SGX. And I earlier mentioned the protected file feature, where you can automatically encrypt, decrypt your files in the manifest. It protects both the confidentiality as well as integrity of those files. So As you heard in few of the other talks, enclave entry exits are very expensive. So for performance critical applications, Graphene supports this exitless mode of operation. So this is just one of the few features that we have added in Graphene for performance enhancements. We have a bunch of hooks and the manifest options to not only better understand your application's performance and also enhance it. Manifest gives you those choices. For example, if you want to bring in reserve some pages in the heap and bring in a lot more pages at your load time versus runtime. So Graphene provides you that flexibility via manifest switches. Graphene is one of the very few frameworks that supports full multi-process applications by providing full fork support. So SGX does not provide shared memory. So fork from inside an enclave, Graphene basically will create a brand new process, create a new enclave, do the checkpoint, and migrate the state of the enclave securely. And Graphene also automatically integrates with Docker containers as a way to deploy your secure applications. So let me give you a little bit insight into attestations. So by itself, attestation only proves to a remote verifier that the correct code is executed and that the data is protected in a protected enclave. But in almost all the cases, you need to create a secure channel with a remote TE, and in most cases also provision a secret. Uh, so with that in mind, we actually have a three-tier approach in Graphene. The attestation is exposed via this dev attestation pseudo file system interface. So this interface allows users to extract the report or the code for local and remote attestation. And under the hood, Graphene sort of integrates with various backends to provide you that report. But at the second level, Graphene also already supports a secure channel establishment. And this basically builds on our previous work where we integrated remote attestation with TLS by embedding codes inside the CERT extensions. And Graphene also supports a third level for secret provisioning. So this builds on top of the first two. But with a simple manifest entry, you can enable attestation to a verifier as well as provision secrets in Enclave without any changes to your application. So this code can run even before your application starts off. And the second feature that I want to highlight is the support for Docker containers. So we have this tool called Graphene Shielded Containers. So it effectively allows you to take a simple Docker image and automatically run in Graphene. So GSC takes a Docker image and it also optionally takes a manifest where you can specify your memory and parallelism requirements, how many threads you need, the size, but it's an optional feature. If you choose not to provide any, it can use certain defaults. So you can start with just a vanilla Docker image. So this given these two, GSC basically creates a graphenized Docker image. This new image now includes application, but it pulls in the Graphene runtime, and it also automatically generates this manifest. So this manifest generation is based on the observation that a container already packages the minimal runtime for that environment. And so we use an overestimation scheme and pull in everything that's packaged in the Docker image in the manifest as the trusted files. Now all SGX applications need to be signed. So basically GSC builds the image and signs the image, and at that point you have a new Docker image, and when you give that to Docker run, it effectively runs it like any other Docker image, but all of your code is pushed inside the application in the Docker container is pushed inside in the Graphene. Yeah, so let's try to put all this together. So like I said, Graphene can not only run this unmodified applications in Docker containers, but really gives you this end-to-end tools and framework to build the protected solution with the touch of a button. So let's look at this example where we want to run an object detection service in an untrusted environment, and there's a desire to protect model IP as well as user private data. So you start with a vanilla Docker image, and encrypted models and the input data. So with GSC, this application in the Docker container can be automatically hosted inside the Graphene. And so before graph application gets control, Graphene sort of generates these uses the attestation interfaces, gets a report generated, sends it to a relying party that verifies it and provisions the secret, say the key for the model and the input. And at that point, Graphene transfers control to the application, and the application runs as it would. It just reads the model and input, but it automatically gets decrypted. Application can work on it and then generates the output, which is again automatically encrypted and put back. In this, I used a simple model or simple example where we had only one key, but you could have different keys for the model and the data, and you can extend this to your needs. But this gives you a very basic framework to build most of your applications. So there's a link on our GitHub to actually experiment with this tutorial. Okay, so Graphene is can actually support a lot of usages, and more usages are emerging by the day. There are quite a few startups or other corporations experimenting with Graphene and building their solutions. So that's why we really want to get Graphene to a production readiness state soon. Some of the examples I want to highlight is the one I just showed, which is protected machine learning and AI. Protected federated machine learning is an important use case where your data doesn't move, but you still have to protect the integrity of your computation. And protected analytics, there are a lot of usages around multi-party confidential data computing and collaborative data processing. A lot of them end up using enclaves and specifically Graphene for your data confidentiality and integrity of the compute. The other interesting use case that's emerging, and we have done some work in the space in Intel Labs, is protecting virtual network functions. And this is really it's emerging as a use case for 5G security. Another use case is around protected decentralized computing, where you want to run your compute on these arbitrary computers that may join this decentralized network. And again, Graphene is being used as a place to provide a trusted execution environment. And there are many more actually. So I guess just hope that gives you some idea of where we are at with the Graphene project. So just to summarize, the initial port was released in 2017, but the community really came together in December 2018 when Golem and ITL joined the project, and we put together the governance structure for the project in place. And so since then, we did an early release in 2019, but we realized we had a lot more work to do. So since then, the team has grown quite a bit, and we have made significant changes in the project. Almost all the files in the project are modified. The good news is we have added as much code as much as we have deleted due to sort of refactoring and cleanup. So our TCP really doesn't change. And we have about 30, actually we have about 50 plus authors since the lifetime of the project, but 37 authors since in the last 1.5 years that have joined the project. Most of the code has been reworked. So if you looked at Graphene, say a year or two ago, take a look. It's a very different code base today. So future-wise, like I said earlier, we want to continue to develop towards production readiness in Q2. Q2, Q3 timeframe, and main goal is really to improve the tooling and documentation. Big focus has been around improving the performance. While I'm not sharing any performance numbers here, again, I'm quite excited to see the results. They're quite exciting, and you just have to wait a little bit to see those after the Ice Lake launch. And we are also looking at integrating with future cloud-based deployments, like, for example, Marble Run already integrates with Graphene. There's other integrations happening. Of course, we just want to continue to grow the runtimes and the workloads. The other couple of things we are exploring, especially in the labs, is to extend to protect communication with accelerators, and also explore addition of future TE backends, because Graphene's modular architecture is fairly suitable to do that. Okay, yeah. So with that, I'm on my last slide. We welcome contributions of all type from the community. We invite you to join us and try running your workloads with Graphene. And we want to hear from your experiences of using Graphene. Email us or file issues, but also we want to hear success stories. Sometimes, if Graphene just works out of the box for you, please do let us know. Yeah, with that, I will thank you very much. And here are a few links if you want to go check it out. That's it. This is my last slide.
Thank you, Mona. Thank you so much. That was interesting. Felix is also back. We have some questions and we have time to discuss them here before we go into the breakout sessions.
Yeah. So there was a question regarding performance. I touched on that, but I don't know. Is there a rough number you can give us, like, or some typical performance overhead workloads?
Yeah. So I think it really goes back to earlier we heard from I guess the Oculum guys. It really depends on your workload. There are some workloads which are really more CPU bound, and if you read in the data and then you're returning just the numbers like machine learning, inferencing, training, you can see very close to native performance. But then there are other IO bound workloads. And while by the way, Graphene, we have done a lot of work also to use sort of this idea of exitless and the producer consumer queues, say with GPTK. And so, but some of those may require small changes to your application. But Graphene's goal has been to run completely unmodified applications. So with exitless, we see even with the IO workload, we see some good numbers. So I think I would just wait to quote any numbers here. Yeah.
Okay. There's a question from Amar. Are Graphene shielded images an OCI compatible container?
Graphene images, yeah, they are just basically Docker images. For all practical purposes, it's just it packages Graphene inside it. So it is just like any other Docker image. Yeah.
Okay. A question from my side. What are the key limitations of GSC? Are there certain things that just don't work, or are there edge cases, or can it just convert anything?
Yeah. So we can talk more in the breakout session, and you can ask those questions to both Anyo and Dimitri. But from what I understand, is that we have the latest bug fix with the pull request, which just happened last week. GSC, we think GSC can run majority of Docker images. Except, of course, Graphene has to support all of those system calls. If you have a Docker image where certain system calls are not supported, you'll find other issues. But as long as that application is capable of running in Graphene, that GSC should work, is what my understanding is.
Okay, that sounds great. I also like the dev/attestation abstraction very much. How does it work again? So you have this virtual device, and then?
Yes. So it's actually very cool. It really simplifies the attestation interface for you, right? So we have this dev attestation device. You just open it, and effectively you just specify your user data, and then you can just say read the report, right, or read the code, depending on if you want local attestation or remote attestation. So you just write certain point parameters that you want to pass, and yeah. So it is, yes, I am very excited about it, and yes, very cool interface, I think.
Yeah, is it a recent addition?
I think we have had it for I don't know, a couple months or maybe 3 months, something of that order. Actually, it's been work in progress for a long time, but finally, yeah, the full function in its full glory, it showed up only recently. Yes.
Okay, great.
Do we have any further questions? I don't think so, right?
There's a question regarding production readiness and known holes or vulnerabilities in the attestation protocol, or is it already end-to-end secure?
Can you In the vulnerability, well, like I said, we use the SGX attestation, and then we use TLS for the secure communication. And you automatically, there's no point sort of building a brand new protocol. As long as you trust TLS, I would say you can trust the attestations coming on it. Yeah.
Okay, yeah, makes perfect sense. Okay, great.
Okay, perfect. Thank you so much, Mona.
Thank you.